बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश्रहली सदरी व यस्सिरली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Assalamu alaikum. Today we will cover section 2.6 motion diagrams from the book Physics for Scientists and Engineers with Modern Physics by Serway and Jewett, 10th edition. The concept of velocity and acceleration are often confused with each other, but in fact they are quite different quantities. In forming a mental representation of a moving object, a pictorial representation called a motion diagram is sometimes useful to describe the velocity and acceleration while an object is in motion. A motion diagram can be formed by imagining stroboscopic photograph of a moving object which shows several images of the object taken as the strobe light flashes at a constant rate. Figure 2.1a is a motion diagram for the car started in section 2.1. Figure 2.10 represents three sets of strobe photograph of car moving along a straight roadway in a single direction from left to right. The time interval between the flashes of the stroboscope are equal in each part of the diagram. So, as not to confuse two vector quantities, we use red arrow for velocity and purple arrow for acceleration in figure 2.10. The arrows are shown at several instants during the motion of the object. Let us describe the motion of the car in each diagram. In figure 2.10a, the images of the car are equally spaced, showing us that the car moves through the same displacement in each time interval. This equal spacing is consistent with the car moving with constant positive velocity and zero acceleration. We could model the car as a particle and describe it with particle and a constant velocity model. The red velocity arrows are all of equal length and there are no purple acceleration arrows shown because it is of length 0. In figure 2.10b, the images become further apart as time progresses. In this case, the red velocity arrow increases in length with time because the car's displacement between adjacent positions increase in time. These features suggest the car is moving with a positive velocity and a positive acceleration. The velocity and acceleration are in the same direction. In terms of our earlier force discussion, imagine a force pulling on the car in the same direction it is moving, it speeds up. In figure 2.10c, we can tell that the car slows as it moves to the right because its displacement between the adjacent images decreases with time. This case suggests the car moves to the right with negative acceleration. The length of the velocity arrow decreases in time and eventually reaches 0. From this diagram, we see that the acceleration and the velocity arrow are not in the same direction. The car is moving with positive velocity but with negative acceleration. This type of motion is exhibited by a car that skids to stop after its brakes are applied. The velocity and acceleration are in the opposite direction. In terms of our earlier force discussion, imagine a force pulling on the car opposite to the direction it is moving, it slows down. Each purple acceleration arrow in path B and C of figure 2.10 is the same length. Therefore, these diagrams represent the motion of particle under constant acceleration. This important analysis model will be discussed in the next section. Figure 2.10 motion diagram of a car moving along a straight roadway in a single direction. The velocity at each instant is indicated by a red arrow and the constant acceleration is indicated by a purple arrow. Figure 2.10a, this car moves at constant velocity, zero acceleration. Figure 2.10b, this car has constant acceleration in the direction of its velocity. Figure 2.10c, this car has a constant acceleration in the direction opposite its velocity. In figure 2.10a, the car moves with constant velocity. The velocity vectors are of the same length and the distance between the car is the same. Therefore, it represents constant velocity model and zero acceleration model. In figure 2.10b, the velocity vector and the acceleration vector are in the same direction. the acceleration vector is constant and the velocity vector keeps on increasing. Therefore, the car speeds up. The distance between the car keeps on increasing. This is equivalent to the situation in which the car accelerator is applied. In figure 2.10c, the velocity vector and the acceleration vector are in opposite direction. In this case, the acceleration vector is constant and the velocity vector keeps on decreasing. This is equivalent to the situation when the brakes are applied and the car eventually comes to stop. May Allah bless us all. Thank you for watching. Allah Hafiz.